So we're going to talk about the end of the universe in later on in the course.
Okay.
But I guess I'm curious to know, is there any other alternatives to A and B? You know, could it just be that general relativity is wrong in some way that we haven't anticipated?
Well, we don't know. The great thing about not knowing is you don't know, and that's fine. We don't know. We don't know about quantum gravity. We don't have a theory of quantum gravity, and that means we can't say what happened at t equals 0, the Big Bang. And it may be that quantum gravity would reveal something. In fact, we fully expect that general relativity will change. At microscopic scales, it will change. The problem, however, is that the scale of this energy density is not the scale at which quantum gravity would naively produce effects.
Right.
So if it was, when we say, there's some quantum phenomena that explain this, this scale is so much larger in distance scale and smaller in energy scale that really is inexplicable. But and the other thing I should say is when Einstein put in the cosmological constant, he put it in as a fudge factor, because he was trying to solve a problem that didn't really exist. He was trying to explain a static universe, and the universe wasn't static. But it was just a fudge factor for a long time. But but the point is, now that we understand quantum mechanics and quantum field theory, even if Einstein hadn't invented it, someone else would have, because it is a property of all quantum mechanical systems, even a harmonic oscillator, that it has some ground state energy, a half h bar, okay, and a half h bar omega, depending upon the nature of the oscillator. And so it is incredibly natural to expect on quantum mechanical grounds that empty space should have energy. That's not what's weird. What's weird is why the value is so low.
Yeah.
And usually, if you're a theorist, usually the ultimate answer is not what you expected. That's why we need to keep on exploring the universe. So ground state energy is one possibility. Quintessence is a very unlikely, something that's really changing. A field that gets stuck is a possible answer, but again, why it has a value it has is strange. And the other possibility is something else. And nature may pick something else. We just don't know the answer.
So you haven't really got back to the original puzzle of why there's this coincidence.
Okay, let's get back to that, because that is a real, regardless of what the cause of dark energy is, it is an incredible coincidence that normal matter and dark matter have around the same energy. And by the way, I will say that was one of the motivations of quintessence, because if you have a field that's somehow changing along with matter, then you might be able to make those two things remain close. Again, as a theorist, I would argue that there's really no good way to do it, and it was mostly public relations that suggested you could. I've looked at that a lot and thought of it a lot, and I don't think there's any good way to do it. But that's one possibility. Just because I can't figure out a way to do it doesn't mean it doesn't happen. But the other possibility is that it really is a coincidence. But I want to go back to when we were talking about inflation, to the realization that inflation says there could be many universes. And they could, and maybe in each universe there's some field that has some expectation value that's different at low energy, and therefore there's different late time expansions. It has been realized, and I think Steve Weinberg was the first one to point it out, that if you look and say, well, there's an energy of empty space and there are many universes, if you make those two assumptions, that it's different in every universe, then it's true that if the energy of empty space were much bigger than it is today, say 50 times bigger than it is today, then galaxies would never have formed. And if galaxies wouldn't have formed, then stars wouldn't have formed, and people wouldn't have formed, and astronomers wouldn't have formed. So we can say the universe is here because there are astronomers that can measure it. It sounds like design, but it's not. It's kind of cosmic natural selection. We'd be very surprised to find ourselves living in a universe in which we couldn't live. But it may mean that ultimate physical quantity that describes our universe is an accident, and in other universes is different. And it may mean that life like us can only evolve in a universe in which the energy of empty space is not much bigger than it is, and that's why it's so absurdly small. That idea, which goes by the name of the anthropic principle, it's really doesn't deserve the word principle, is a possible idea. But even so, I want to point out that many times in the last century, the anthropic principle has been employed to explain otherwise inexplicable results. Later on, we always discovered a fundamental theory that explained it. So far, it hasn't got a good track record, and if I were betting on it, I wouldn't bet on it. But also, there's another aspect which isn't emphasized enough. It is true that if the energy of empty space were vastly different than it is, then life forms like us wouldn't form. It doesn't tell us that no life forms would form, first of all. But secondly, that's not the only parameter in nature. The energy of empty space is just one. What if in other universes the mass of particles were different and the energy densities that result were different? We don't know the locus of all possibilities. And so we don't know that in a universe with a vastly different cosmological constant, if the other parameters were different, that life couldn't form. And since we don't know, it's rather pretentious to claim that this is the only possible universe in which life can exist. And therefore, in fact, you can, and I've done this, I've written papers on this, as have other people, you can imagine changing other parameters in a way that would predict that the cosmological constant should be very, very different on average for life forms to exist than the one we measure, making us very strange instead of very natural. So this is all kind of metaphysics at this point. We don't know. And that's one of the reasons why it's so exciting to probe inflation, potentially experimentally, because when we learn more about fundamental particle physics, we'll find out which of these ideas goes out the window.
So, in terms of it being metaphysics or not, it sort of is metaphysics, but the one reason you might say it isn't is that Steven Weinberg, when he came up with this idea, predicted in advance the value of the cosmological constant. He didn't get it exactly right, but it's pretty damn close.
Yeah, the model says it should be about the same order we see now. That is really remarkable. That is absolutely remarkable. And maybe it's true, or maybe it's just an accident, because it frankly, from a theoretical perspective, if you have many different universes and the laws of physics are different in each one, it's hard to imagine why only the cosmological constant would change and no other parameter. And Steve's calculation, which was remarkable and prescient and simple, requires that to be the only parameter that varies in all different universes, and that seems kind of unnatural. But it is a remarkable statement that in 1987, Steve, I think that's when he wrote that paper in Reviews of Modern Physics, said that if there's an energy of empty space, it should be about the amount we see. I mean, frankly, we knew it couldn't be much larger already.
Right. And so, it wouldn't exist.
And so, as a theorist, I would say it's often, it's easy to predict things just below the threshold of observation. And we've done that a lot. We used to predict density fluctuations, which were larger, and then the observers said, no. We always predicted to be a little bit less, and lo and behold, they were a little bit less. And the cosmological constant is about as large as it can be for someone like you to have stumbled upon it, frankly. Yep. If we're much smaller, we'd never know about it. And by the way, well, we'll get to the future of the universe later, so I don't want to get there now.
Yep.
Thank you, and we'll have you back again later.
Okay.